Okay, so there comes a time when you have to set aside all your humility and load up on a nice, juicy slice of credit. And this is one of those occasions. Scott Walter and Gustav Andersson have long been advocating on this channel for the Tesla Optimus team to just consult a hand surgeon. Why? Because the hand is where the mind meets the world. And if Optimus has to become the world's best generalized humanoid robot, the Optimus team of engineers needs to mimic the biomechanics of the human hand. Gustav Andersson, as it just so happens, is a hand surgeon and associate professor of anatomy in northern Sweden. Scott Walter, as you probably know by now, is a mechanical and aerospace engineer and two-time founder of Robotics company. So, gentlemen, do you feel vindicated?
Well, of course, no, but I mean, we pounded the drum back in October, November last year, and I guess we can take credit that perhaps some of the Tesla team saw our comments or watched a snippet of our videos, or at least they're starting to realize what we realized back then, that there are things that might need to be considered. Even if you have a really strong engineering background, there might be issues that you not always take into account.
Yes, and I've always said that the business end of the robot is the hand, and I've always felt, with the same kind of, let's say, arrogance of the engineers that, we can just reverse engineer this thing and do it, from first principles and figure it out ourselves because we're very smart. But it was only after you first invited Gustav on, Royden, that I realized what was going on, and I think we probably finished that with my things that they should really consult a hand surgeon, because it was that really convinced me. It's like, wait a minute, it's more than an engineering problem. It's really, really understanding that. And I've said that multiple times, not just on this channel, on others. And I have found out that, that it turns out some of these engineers from a variety of different companies actually listen to us sometimes. We'll hear some comments about that. And the other thing I've also felt is that when it comes to walking, they should all be consulting physical therapists, because physical therapists are really good at doing gait analysis, looking at that and identifying, let's say, gaits that are incorrect, and even a hand surgeon, because I think Gustav was the one that introduced me to, what is it, is it Trent-Ellenberg syndrome, which is a kind of a funny sashaying when you're walking, which the Unitree bot tends to do. So there's already a knowledge base out there, and I have a feeling there might be a couple of good hand surgeons in the Bay Area. I'm not sure. I mean, there might be a few. If not, there's one up.
Maybe Elon could just hire Gustav, and we'll have an insider.
Exactly.
Yeah, I think I made that comment the first time, that I work very cheaply or even for free.
Yeah, exactly.
Sweaty equity in Tesla. That's what you need, Gustav.
Right. So Royden, why are you crowing about this all of a sudden? What's the background?
Oh, well, so let's just listen to what Lars had to say over the weekend. There was a Tesla owners Silicon Valley meetup. It was the X takeover, I think, and Lars had a lot to say.
What's been the biggest difference working on, I mean, obviously you guys build the machine that builds the machine, but when you think of like vehicle engineering to now humanoid robots, what is some of either the learnings from, making a car versus a robot, like a humanoid robot?
Yeah, I mean, I would say one of the most interesting things about like trying to build Optimus and manufacture it is like the precision. The human body is amazing. I don't know. Once you start designing a humanoid robot, you sit in a meeting, you just hold your hand up and you're like, how do I do that? And you kind of move your joints around and try and figure out how to emulate that mechanically is really hard. The human body has some amazing things. The team I know just went and visited a hand surgeon to figure out how the human hand worked a little better, and it's crazy to watch and see what the tendons do and how the muscles pull them. And when I was growing up, I always thought working on cars was a bit like being a surgeon, because you got the hoses and cold fluid comes into the engine on one side and hot goes out the other. It's kind of like a heart, and it is not at all the same. it's very difficult to get the precision you need and the response and the tactility. And I think, as Elon was talking about the other day on earnings call, Gen-3, the robots, will be quite a step forward in those kind of things.
Do you pay close attention to how other EV makers, particularly in China, are innovating with different form factors and even features like dancing, ability to dance? And
yeah. I mean, China is a powerhouse of building, if nothing else, right? They can manufacture everything and anything under the sun faster than anyone else in the world. And that's a superpower that they have. But we're as with cars, we're always looking at what other people are doing. But I think we are, even though we're paying attention, like we're grounding ourselves in what do we think is the right solution. And when you look at some of the robots that have followed the Optimus, revolution, I guess, or even the humanoid revolution, I should say, I think they're less generalized than what we're doing, and that's going to spawn a problem for them down the road somewhere. Like as with FSD, we've gone with a generalized solution and trying to make the robot live in the human world that we've spent, I don't know what, 20,000 years developing, right? So yeah, we pay attention, but we don't let it necessarily change the thought process we have.
Yeah, so there you have it. It's all about the best generalized robot, because if you have to deal with a world built by humans for humans, you need to be able to mimic the biomechanics of the human hand. Before we get into the generalized bit and what this entire philosophy is about, the design approach to it, let's just also listen to what Elon said.
Humanoid robot has really made me think a lot about how the human body works. You gain a new appreciation for actually just how awesome a design the human body is. Now, admittedly, I think some parts of the human body could be better, like the spine. Like, why do we have so much back pain? It's very annoying. Optimus has really made me think a lot about how our hands work, how we balance, how we do different things. But maybe more than anything, just how incredible our hands are. It's like, wow. Things that our hands do. Like the hands of Optimus are half or more than half of the electromechanical problem. And the entire rest of the body is a half. Yeah.
Yeah, so that really is so telling. It goes to show just how important the hand is and what a big problem it is to solve, right?
Yeah, and when it comes to the spine, don't challenge sumo wrestlers, as the interview later commented.
Yeah.
Well, Neuralink might have a bypass there.
Yeah, to get some pain relief.
Yeah.
No, but I appreciate that they are appreciating the problem. And of course, we've discussed previously that if you have one goal or one task that you need to solve, then you perhaps you really don't need the humanoid hand. But if you're going to use the tools that we have available, then you need the right tool for the tools. Or how was the quote, Scott?
Yeah. Yep.
Well, yeah, I think someone sent me a post that said Aristotle talked about the hand being the tool of tools. But I think there was a more eloquent quotation from Aristotle, if you want to bring that up. So it's been an observation that what goes back at least 3,000 years or more of how important the hand is, and if you want to be very general, you need to do that. So I can't read it on the screen. I don't have my bifocals on. So Royden, if you can read the quote.
Yeah. So the quote goes, "For the hand is not to be looked on as one organ, but as many. It is, as it were, an instrument for instruments."
Yeah. And this was also the point of view of the early hand surgeons. So we haven't been around for too long, but after the First and Second World War, there was a realization that you don't just need someone who can screw the bone together or someone who can suture the nerves. You needed someone who saw the extremity as a whole. So our American forebears had that point of view, and it spread to the rest of the world when it comes to hand surgery, that sure, the orthopedics are very good at fixing the bone and the neurosurgeons are good at suturing nerves, but you needed someone who saw the whole package with the muscles, bone, vessels, tendons, and so forth. So already early Greeks had the right point of view, I'd say.
Yeah, and
So-
what we'll think about is like we talk about the limbs, that we effectively have 4, or some people say 5 limbs if you count the head, but really each finger is a mini limb on its own. So the human body has what, 5 limbs, and then it's got 10 of these things here, and these are of the same complexity or more than what you have there, which is why it shouldn't be a surprise that half the problem is here, as Elon said. You know, all the, and I would almost think maybe more than that. I would, because all the fine motor skill, everything is going on here. Everything else is about getting the hands to where they need to be, and nothing more. And yes, there's some challenges there on locomotion and balance and everything, and trying to help. But in the end, it really comes down to either you have hands or you don't have hands. And without them, you're not going to be able to do useful work. And again, it comes down to how good do your hands have to be? You know, have we gone overboard by saying that all our robot hands must have 5 fingers?
Yeah.
You know, there are some that are going with 3 fingers, you know, but they will only work in very narrow applications. And how many degrees of freedom have to be in there? So all these things have to be understood. And
what about
I'm
touch?
glad-
What about touch sensors?
Well, touch sensing as well. But one of the reasons why I'm glad they finally, and Lars said they just, I'm like, I mean, you haven't done this before. You've been having all kinds of challenges with this 22 DOF hand. You went ahead and said, oh, we're going to make it just like the human hand, but you didn't bring in someone who would know. And one of the first things that Gustav said to talk to us is like looking at outcomes, patient outcomes, and deciding, you know, you realize I cannot fix their hand to be 100% like it was before, but there's some things I'm going to do which will restore some kind of functionality, and consulting with the patient to try to figure out what that is. And I think it's the same kind of problem. The mindset that you need to have is don't try to design the hand that can do everything right now, but figure out what are really the use cases and narrow on in, and ask yourself, is piano playing really a prerequisite for what the Optimus robot needs to do? Because you do need a certain amount of dexterity there that you may not need in a lot of the tasks you're doing. So while it's nice that it might be able to do that, it could be that you're over designing. And we've talked about that a little bit before, and we'll kind of get into the differences between the Gen 1, Gen 2 hands and maybe what the Gen 3 hands will end up looking like.
Yeah. And I just quickly want to go back to this, the post from Humanoid Hub, where he talks about, where he says, and this is basically referencing Lars's interview, and saying that some Optimus engineers recently visited the hand surgeon. So we have confirmation to better understand how hand tendons and muscles work. It's tricky to mimic the mechanics of the human body. Tendons and muscles, do actuators do the job of both in the hand, or is it going to be a whole new approach? Maybe something like the clone hand.
I mean, there are different, I would say. You have the long ones, the ones that Elon likes to talk about, the muscles in your forearm, which have long tendons, whereas the intrinsic muscles, the muscles in your hand, they're very quite short and barely have any tendons almost, some of them. They're just muscle from bone to bone almost. You have a short tendon insertion. Some of them connect to the extensor, the long extensor tendon, to help with some of the intrinsic or the small fine motions of the hand. So the muscle...
You're going to do a show and tell, Gustav. You're going to do a show and tell.
Yeah, I don't know what I have, but...
It's okay. It's okay. You're just kidding.
I always have my hands available. No, but I mean, so you see the tendons in the middle. These are the long flexors that go up through the carpal tunnel that he talked about and up originating in your forearm, whereas the muscles in the thenar and the hypothenar and also the interossei, which are the muscles between the bones, they have very short tendons in general. So these long ones go from the forearm, and there the tendons in themselves are, I'm not sure how much in the function of the patient, but when we assess patients, we use the stiffness of the tendons to assess whether they have function. So if you relax your hand and you flex it, your fingers will straighten. And that's because the tendons are not just loose things. And when you extend the hand, the fingers will flex because the tendons are quite stiff, so they follow along. The muscles are not moving the fingers now. It's just my wrist that is extending and flexing. So I'm not sure that will kind of be something you have to emulate for your robot, but that's how we function at least. So in certain positions, your grip is stronger.
It's going to function like that. I mean, that's just a basic problem. When you do that, whatever tendons you have going through there are changing their tension.
The length,
and that means the control algorithm has to understand that. That's a problem. You get that for free, Gustav.
Yeah, exactly. And also the strength of your grip. I think I've talked about this, but if you have your hand in this position, you're very weak because your flexors can't flex or tension all the way. Whereas in this position, you have a very strong grip. So some kind of, if you remove the knife of an attacker, you should bend the wrist, the karate teacher always says. But it's important for how you grip your tools as well. So if you have a fused wrist, you don't want it to be in this position, because then the patient will be very weak. And someone with like a cerebral palsy, usually their hand turns into this position. So part of helping them with hand surgery, we position the wrist in a more functioning way. So this is not a good position of your wrist. You need it to be a little bit extended to have a good grip. But when you have this good grip, it's, as I've also talked about before, it might be enough to have this. You might not really need the flexion of the wrist in most applications. If you're a carpenter, you will have a very good function with a stiff wrist that you cannot flex or extend. You just put it in this position and you get a good strong grip to hold your hammer and whack away. So, and that's where you talked about perhaps for the early stages, they don't really need to go into all of these different motions. It might be that they find that certain, like splaying of the fingers, the ab and adduction, perhaps is not important, aside from giving stability to the finger. And there it's perhaps easier to skip doing the greeting sign, and instead you get this what do you call it, the lateral stability directly if you only have like a basic hinge joint. But then you would lose certain grip patterns, because most of the hands you see the fingers flex straight down, like the thing, I can't even fake it, the little finger in all these robots and this one, it goes like straight down towards the palm when you look at these robotic hands. But that's not how we flex our fingers. We flex our fingers towards the base of the thumb like this, and almost into opposition with the thumb. So this is how your fingers flex. They don't flex straight down your palm, but most of the robotic hands out there, they kind of go straight down into your palm, and that automatically makes gripping a ball or a hammer or something really tricky. And when you see them picking up balls, they almost never use these two fingers because they're not in the right position. They always get the tripod grip, and they kind of get like a lateral support of the fourth finger, which is like a lucky side effect, I guess. But they didn't even look at where the fingers are pointing most of these hands. And maybe it's easier to design it like that, but it's not really emulating the human hand. And I guess anyone who had some anatomy background or looked at hands before could have told them quite early, yeah, it looks nice, but it's not how the hand or the fingers actually move.
You're going to have these problems. So how important is a different length of the hands? Because in the Gen 1 Optimus, they wanted to reduce the number of skews, so all the fingers were identical. They were just offset a little bit, but your pinky was definitely much bigger. In your view, is that an okay kind of compromise, or do you think there is something about the fact that all of our fingers are slightly different proportion and length?
Yeah, at least I'm looking at it now from like a trauma or helping our patients, and one of the things that we do not like to see in a broken hand is if you have a big discrepancy in the length of your metacarpals, for instance. A common fracture is breaking the end of your metacarpal, the fourth and the fifth. Someone punches a wall when they're angry, and usually you can take quite a big change in the angulation, like if the bone is not totally straight anymore. But if it's very shortened, then that will affect how they grip things, and it might not be what you're give the same issue if you have similar length of fingers, because we're built in a way and you could perhaps get around it. But I'm thinking in gripping things, and I have my trusty old power drill here. I mean, it's you don't want them to go if this one was longer, it would go all the way out here.
Right.
So our tools are designed from us having different length fingers.
Yeah.
And I can't get away from the thought that there is a reason why we have evolved that way. Certain primates probably have longer, maybe more even fingers, and some of us have a longer, like there is some variation in the length of the index compared to the ring finger.
Yeah, but that again goes back to the point that certain primates that have more even lengths in their fingers would need less functionality. I mean, they don't use too many tools, do they?
Exactly. Yeah.
Okay, so let me just play this video. So this was from a little while back.
Okay, just before we go
ahead.
just take it one more. What about the number of IP joints?
Mm-mm.
Do you think it was a mistake to remove an IP joint and that you need to have both of them?
Yeah, we mentioned this before as well, and I'd say for the fourth and the fifth fingers, you could definitely remove one. For what we're doing, it's nice to have this, but we do IP joint fusion a lot in patients with osteoarthritis and painful like joints in the distal joint of the finger. So we really don't consider that a handicap to make them stiff as long as they are in a nice position. And if you like relax your hand or fingers, you could tell what this should be quite straight, whereas the little finger should be quite flexed. This is like a nice position of the distal joints. So now I can easily grip my hammer. It's not a problem. And here I can get the needle or whatever. Whereas if it's too bent, it might get issues when I'm picking things up. So we do that quite a lot in elderly who have painful joints, and it's really not considered a big handicap. Whereas if you stiffen this joint, then you're in trouble, and this one as well, because then you can't really open up your palm anymore or grip very efficiently. But the distal one, you could really get away with removing that, I'd say.
So how many degrees of freedom do you need in the hand to be able to thread a needle?
Yeah, exactly. Probably not very many. I
don't think you need 22, do you?
Yeah. But I mean, but here you go. And this is what I wanted to play out. In order to do this, to catch the ball, how many fingers do you need?
Yeah. And you see there, he grabs it with 3 fingers, basically. And the other 2 are just lateral support in both of these cases. And I mean, we grab it with all the fingers, and that's also why we need this opposition of the little finger towards the thumb. If the little finger went straight down into the palm now, it wouldn't help at all. We're using this type of grip. And also the motion of the 5th and 4th metacarpal, we're kind of making an arch in the hand, and they showed that with the V3 robot, that they had like a small joint to move the 5th metacarpal, but it's quite far out there. It's not at the base of the metacarpals.
Yeah.
So, and we use this when in all things, when we grip things, we get these soft thenar and hypothenar eminences, the pads, they move towards each other, and it improves our grip. If we didn't have these pads, when you grip a ball or grip a glass or a hammer, we're using this part of the hand in the grip. So if this is totally flat, then you would have to compensate your grip in other ways. And I think that's maybe why you always get this tripod grip in all of these, gripping the ball or gripping the boxes. They never use the 4th and 5th fingers almost.
Right. And then there's the abduction, which is important. That to be able to grab something like this, you want that abduction. If you don't have the abduction, you're grabbing it kind of funny, and it's not really a good firm grip.
No.
So that's partly coming from abduction. And then the other thing you're saying, part of it is also coming from the fact that the palm is able to unflatten itself, I guess you could say, to be able to come around. But again, you don't necessarily have to have all that movement to be able to grab something like this and grab it securely. We're just used to that's what our hands are able to do. They're very deformable. And in any kind of engineering, and again, with the hand surgeons, you have to make the decision of what kind of functionality are you willing to sacrifice in order to still maintain a reasonable amount of function.
Yeah.
Right. Okay, so Scott, this question is coming your way. The electromechanical problem that needs to be solved for a wider audience. Can you just explain, please, what Elon meant by that?
Okay, so electromechanical, he's really talking about pulling on the puppet strings. So you've got a lot of forces you have to apply, and you need to be able to make them compact enough that they can fit in someplace. Okay. And you want to make sure you do it without having excess mass, excess volume, and of course, excess power requirements. And it almost sounded like he was alluding to the fact that the hand might be taking half of the energy. I mean, he was a little bit. I would certainly think the first time I heard it, I wasn't quite sure, and I listened to it a couple of times. It could be that that if you're getting a lot of the dexterity out of it, there is a lot of power and energy requirements coming out of this. Now, you've heard me say this before, about the Fermi paradox of robotic hands, that if they exist, where are they? Because we've seen YouTube videos for like easily 10 years or more of really great robotic hands, animatronic hands, and everything else that are very, very convincing. And part of the reason they're not on an actual robot hands or any robot, is they're not practical yet. They don't have the robustness. They're very hard to control. And a lot of times you're seeing a hand moving around like this, but what you're not seeing is the huge box and the big control system that's right underneath it. And what you're talking about is trying to take something which is really, really big and shove it right into your forearm. So, and that is a very difficult packaging problem. Reading between, a lot of the tea leaves that we see out there, and some of the comments were there. And I think about a month ago, there were some articles that came out of, I think, a publication in China talking about the difficulties they were having, is that they weren't getting the grip strength that they needed in the hands, because each of those puppet strings has its own little linear actuator. And I mean, we're talking a little linear actuator, and there's 24 of them. So a stack of 3 of them around there, they can only be so big, and they can only develop so much force. And I think that's what they were finding, is that they were not able to get the strength that they needed. My suspicion is the strength may not have actually been so much in whether they have enough strength in flexion, but it could be that they don't have enough strength in the ab and adduction to get the dexterity and the control they were looking for. And this is something I want to cross-examine Gustav a little bit about. It's like, how are we so good at being able to lock our abductors when just about every robot hand I see out there is really sloppy on it? And we talked about that with 1X actually did basically a CMJ fusion, right? Right down here in order to keep the thumb in a good position to be able to do pinch kind of maneuvers.
Yeah, and I should probably know the biomechanics of it better, but I mean, it is the small intrinsic muscles that are extremely important, and they control the splaying and the lateral support. It's not the muscles up here, and I'm guessing they would have a lot of issues with trying to control this with muscles up here, when it's like you need short reaction times and it's really small stabilization of the joint. So I think that's why I thought perhaps they could have this piston design that they have for the wrist. Perhaps they should have that for the MP joints instead. I don't know. To instead have a very stable abduction and adduction control, and not the finicky tendons and strings trying to kind of hold this. And we saw it already just recently in the clone bot as well. When it grips the ball, the fingers kind of cross over, and they don't really manage to control the ab and adduction as well. And they actually have the muscles within their hand in the clone bot, I think. So this was the original, or the first tech demo, I guess. And we never really knew here if they were going for this at all, or if it's just hinge joints in the MP joints in this old robotic design. They did, however, show the thumb being able to move in a opposition and antiposition in that old Tesla bot. But here, they don't really have control of the stability.
Exactly. So the original, so this is the Gen 1, and the Gen 2 is very similar kinematically. You have 2 degrees of freedom in the thumb, and then you just have the flexion and the extension, and that just with springs that they're putting in the one IP joint, that's kind of controlling, but they get that clawing motion because they have only one flexure coming down, so they can't really close the fingers straight and then come in like this. They need that to come down. Now, the 22 DOF hand, in theory, fixes that problem because they have the extensors that will allow you to kind of pull it back to be able to get it. And then again, because now they added that degree of freedom to move back and forth, that becomes a problem. Now, the other thing that you sort of mentioned is that, as we know, is that if you move your wrist, your tendons are basically being tugged on. which is causing other fingers to move. If you've got tendons down here in your forearm that are trying to keep the abductor in place and your hand moves, that means your fingers are going to like do that, right? Or do this. They're really hard to lock in. And to understand how important that is, that if you're going to do a pinch maneuver and you're going to apply a lot of force, you can feel it down here in your knuckle. Just pinch on there and you're going to notice you've got to do a lot to hold it in there. Otherwise, your finger is going to slip off like that. And if you don't want it to slip off, you need something to hold that in place. And their solution has been to have 2 tendons down there. And the reason you have 2 tendons is because tendons are good in tension, but they're terrible in compression. So you can't push on a tendon to try to hold something in place. You've got to pull it that way. So if you're trying to prevent it to go one way or another, you've got to have it there. So again, I've used the analogy. It's like trying to keep a horse that's wanting its head to go back and forth. You're constantly pulling on. All you can do is tug on a rein. You can't push on it. You can just relax the tension, but you can't increase the tension as you would need to be able to keep that in place. And that thing is fighting you because you've got all sorts of forces that are on there you're trying to hold in place. That's going to be difficult to lock down. There is a solution. I thought about this would be a solution, and sure enough, I saw it at the Automatica show in Munich. There's a company there called Agile, and they make a lot of different cobots. It also had a hand on display. I'm sure others have thought about it, and they actually had like fingers that it comes completely off, so you can build your hand up and remove the entire finger unit with it. And they had 2 very small actuators in there that had tendons on there. So they had the flexure and they had the extension to be able to do that. And then they had also control of abduction. And you would think, oh, if they got control of the abduction going this way, they're going to need 2 more, right? Because they're going to need the tendons to do ab and add to do it. It's like, nope, they had just 1 motor in there. And did they do it with a tendon? Nope, that's a mechanical linkage. They basically just use bevel gears coming on up there, and they say, look, we can just do this, and then for position control, they can get it there and they can lock it in. And you don't have to worry about it. So,
and that's the way we solved it as well with the hand. I mean, we have the muscles here. We don't have to bother about this movement when it comes to the ab abduction. So if I do this, it's the same tension in these muscles. So I'd say try to, and I don't know how to design these actuators. That's not my field of expertise, of course, but it would be nice to have some kind of intrinsic actuator, and then you can have your long flexor tendon design.
They kind of get the room, because think about it. On the original hand, they put all 6 actuators in the hand. They were just there. And now they decided, oh, we're going to put all the puppet strings down here. So everything is down here. Basically, there's nothing up in the palm except the raceways for running all of the tendons through there. So what it might mean is that depending on how you do the routing, maybe there's enough room to do something like that. The other thing you can potentially do is, do you really need to do live long and prosper? Or do you just need to display and then bring it back?
What sort of functionality does it serve?
Well, I mean, if you need to play the piano and do other things, you need to be able to have independent control on that. But the majority of the cases, we just need to have either the fingers out or in, out or in. The other thing, when this was clever from the Sanctuary video or Sanctuary patent, their middle finger is actually locked in place. So you only have ab and adduction on 3 of your fingers, but you get the same effect. And what they did in the original patent, later, what they actually built was different. The original patent was they had 1 tendon that basically you pulled on that made them all open and made them all close, because it wasn't clear that you needed that much control. So that's one way of simplifying it. And I think there's a couple of things that we need to think about for the Gen-3 bot. Is they've talked about it, that they've finally got the design, they're getting ready to develop the prototype, they're very happy with it, and all Elon has said is that basically almost nothing stays the same. They're changing from head to toe, which is something I was expecting them to do a year ago when they're working on it, but now it looks like they've decided. Now, what does that mean? I have a feeling what that means is we've had the debate of, do they do linear actuators or rotary? What's the best way to go? Most of the world is going rotary. I have a feeling the Gen-3 is going to be all rotary, with maybe a couple of minor exceptions for like the wrist and for the ankles. But I think everywhere else it's all rotary, and the linears are out. That's going to be it. So it's going to be much sleeker. They're realizing the world's hips design. Now the question is, like, but are they going to drop tendons? Are they going to have a tendon-based hand? Well, I think it's pretty clear from what Lars said and from what Elon said is that it's definitely going to be tendon. Yeah, it is definitely going to be a tendon-based hand. The question is whether they're doubling down on the 22 DOF hand or whether they're like stepping back and saying, wait a minute, let's approach the problem a little bit different, because I think the pendulum swung too far. That they said, our Gen 1, Gen 2, it's too simple. We need the other IP joint. We need to have this and that. And then I think everyone came in and just, too many cooks in the kitchen or too many requirements. Everyone just said, yeah, we're going to do this.
It's kind of the opposite of what they've been doing so far with their first principles.
Yeah,
instead of taking stuff away, they're just adding.
And so what ends up happening is sometimes they say you add too much and then you got to start taking away and bring the pendulum back. My suspicion is they're going to realize we don't need a 22 DOF hand. They're going to decrease it. Now, what do we mean by DOF? Please, there's DOFs and there's actuators. Usually when they're saying DOFs, we're talking about the number of joints, the total number of joints that can move. And then there's the actual number of actuators you put in there to be able to move those. I would say they could get by with like a 16 jointed hand and then have 7 actuators. Just give you this and that going back and forth. And then depending on what they want to do, if they want to have a bit more control on the fingers opening and closing, maybe they have to add a bit more. But it sounds like Elon is still fixated in this idea of the puppet strings. That they're definitely going to go in there, but they may beef them up so they get a bit more strength in the gripper. And I would just completely rethink how you could do abduction. Because that seems to be everyone's Achilles heel, even though the Achilles heel is down there, but it's up here.
And I mean, we probably don't need too much strength in those. You need to be able to use them, and they need to quickly react. But the strength of these muscles are very. I should perhaps learn how strong they are. But I mean, the strength of your pinch is much smaller than your gripping strength.
So even when you're doing a deadlift, for example.
See what I think is happening is that, first of all, because they're doing it with a tendon, and if you look at the little joint that they have that's down there, so they've got a joint that's right here, and they have a tendon coming over here and tendon coming over there, and the lever arm for that thing is really small. We're talking about maybe half a centimeter. Okay, that's a very small lever arm, and that means you got to tug on that thing in order to move it, and that's basically the torque you have to put around there has to now match the torque that's up here. So if I push up here with, let's say, a force of 1 pound, and I've got a lever arm here down to there, which is almost 20 times what the lever arm is of that. That means whatever I'm pulling that thing down is going to come up with like a 20-pound force in order to counter that 1 pound force that's on the tip that's happening when I push my fingers down, because when I'm pushing them like that, there's probably a lot of force. So in some ways, it's almost like the flexure is creating the force that now your abductor has to fight. And it's simply that the math is killing you there. You got to get a bigger moment arm to be able to do that. And the best way to do it is probably do it through like a pure mechanical linkage that would be able to get you positioned a little bit better. That's sort of my thought process of what they could do to improve it.
I mean, if you want to, I also thought in being that perhaps you could have one actuator doing this and one doing that or whatever. But then I guess in some cases when you're trying to grip your key card, you're using the abductor of your index finger to kind of counter force of the thumb, and then that's just one actuator. Then you would open up your palm while doing that, right? If you only have one playing, so then it would look like this when it's gripping the key card, and maybe that's not the end of the world, but it would perhaps introduce new issues when you're going in to do something in a tight space and your fingers are spreading out. You need it to kind of hold together.
That's and of course the thing is you could decide that one of them has full control and the other
index is probably the one you would want to.
So I think there's a way of attacking the problem of looking at what are all the grips that we typically need, and how do we get there, and how do we minimize the degrees of freedom necessary to do that, period, and then come up with the strength. And that will probably dictate better how many you need to have. But right now it seems like it's well, we don't know, so we're just going to go completely general when they haven't narrowed it down to say, you know what, every single actuator that's in there's going to be a guy arguing for and another guy against. see who comes up to win to say, oh, the pinky doesn't have to abduct. There's no reason, or maybe it does, or maybe these. So they should be looking at it from that standpoint. And I don't think they have. I don't think they've had enough people. I felt you need to go through and have someone look at every single joint in your humanoid bot. And the first thing that everyone on that team has to do is explain to me, what does it do? What's the purpose of that joint? What's the purpose of shoulder flexion? If you can't tell me what the purpose is of shoulder flexion, you shouldn't be designing a humanoid bot, period. Now, once you tell me what the purpose of that is, then tell me, why do we need abductions? Then you need to be able to rank them. That's like, take every one of those joints and rank them from top to bottom and tell me which one's the most important. And if I said I had to take one out, would you be able to get it out? And what are those purposes? I'm not sure that these teams have had those kind of discussions. It may seem like a philosophical discussion, but it's an extremely important one, especially when you start looking at the hand design, because that's even more complicated. That you've got to be going and arguing, what does every single joint do? What's the importance of it? Do I really need it? And as Gustav said, well, maybe we only need 2 IB joints here, but the others, we only need 1 at each, and then these can have 2.
Yeah. And just going back to this post from the Humanoid Hub, he says the Chinese supplier is reportedly saying Tesla is testing at least 3 different technical approaches for the hand. So it seems it's completely aligned with what you've been saying. There seems to still be an internal tussle of sorts, and maybe just every engineer out there in the team is saying, we need this, we need that. I don't know if it's the optimal way to go about, and then because then that delays the entire production line, and the timeline goes askew. So it seems it's as if it's still quite chaotic, and it's like, the takeaway from the Tesla Owners Silicon Valley event was pretty positive. I think pretty much everybody thought, okay, we're sorted with Gen 3. They know what they want to build, but evidence suggests otherwise.
Yeah, and they delayed the timeline quite substantially.
Correct.
And of course, that's the way it always is with Elon's very optimistic timelines.
Yeah.
But I think a lot of the analysts and the YouTubers were a little bit taken aback that, it's not going to be the thousands this year and the tens of thousands next year. It's at least 1 year off, or 2 perhaps. And,
yes, easily, and that's something that we heard the very optimistic projections of internally 10,000, but more than likely it was going to be 5,000. That was the official statement that came out in January, and then here we are in June, and already it's like, whoops, we're completely scrapping that design, and we've got a new design. They don't have a prototype yet. They've got a design lock, kind of, yet they're still visiting a hand surgeon, so they probably haven't quite locked down exactly what the hand is. I suspect it's going to be somewhere between the 22 DOF and the Gen 2 hand. But somewhere along the way, it's like, they know that you don't scale a crappy product. And they were showing us pictures of them getting ready to scale and all that stuff. It should have been obvious in January that they were having problems. I can't believe it took them till April or May to discover there was some sort of issue. And then finally in June that they're trying to rectify that. So something really happened along the way, that a lot of balls were dropped, and that, now it looks like, Elon is back in charge on that. So he'll probably be able to turn that part around. And it looks like Lars is going to be looking more at the manufacturing. I have a feeling he was like a peripheral. Clearly they're always consulting around there. They talked about how that works, that there are no silos, that everyone works around everywhere. So I'm sure he was kind of consultant, but I think he was also preoccupied with like the Cybertruck and the Cybercab and a bunch of other things that he wasn't really able to full-time dedicate it. And now he's probably looking at that, and he's probably saying, all right, guys, you want me to build this? Does the thing work? He's probably going to ask us.
And do we have the suppliers? The dancing, the way it danced back in April or May or wherever it was, I felt that it doesn't need to move better than that when it comes to everything aside from the hands. But then the question is, do they have can they produce the actuators? Do they have the screws? Do they have the material? So it's like,
they don't know yet. That's the problem. all of the suppliers right now, they're waiting for direction on what they should do. So at this point, the people that are thinking of ramping up for the linear, they don't know if they're going to go linear. So they're doing a pause right now. They don't have the prototype yet. And then, the prototype's going to have to go through a lot of testing to see what's kind of going on there. So again, it's like early next year before they're going to be saying, all right, we can start telling the suppliers. And the question is, are the suppliers going to be ready to ramp like that? Or can they kind of do that at the same time? So they have to start sending the signals to the suppliers. What kind of actuators are we looking for here? And have they nailed that down yet? Because it sounds like they were having a lot of issues with overheating of the actuators, of reliability of the actuators, a lot of problems they were not expecting. And maybe they've ironed that out right now, and maybe that was a supplier issue, maybe that was a design issue, maybe it was a little bit of both. But until they get that, it's going to be hard for them to ramp. And the thing is that even though Tesla is vertically integrated, don't kid yourself, they get a lot of stuff from tier 1, tier 2 suppliers constantly, and that a lot of times they do the final assembly. So I've known, a lot of other people have known, and it was very clear that this spring, it's like, oh, guess what? All the actuator components and everything are coming from China. They're just having, the final assembly. And I think that's actually what they're doing is they're not buying from one company. They're buying like the reducers from one, and then they're buying the motors from another, and then putting them in there. And then I'm not sure where the control boards are coming, whether that's something they're actually manufacturing in-house or whether they have another supplier for that. But typically, they don't want someone to see the whole thing. So they're breaking it down into little chunks and then putting them together.
But you, Scott, you have you have your head, what do you call it, ear to the ground, or what's the saying?
I was just about to say this is why we love
companies,
talking to you, Scott, because you just keep us grounded.
I mean, like Figure and the others,
all
what
the
are they
hype.
saying about this? Do they also feel the stress of not having the suppliers ready for them? Or, I mean, the other humanoid, or are they not planning on scaling to this?
They are as well. And so all of them, they have, a different supply chain, or they may be working with some of the same ones, but it's all based around their designs. So the suppliers are going to be producing like a harmonic drive of certain specifications that are going to be coming directly from those humanoid companies, and then they're kind of scaling up for that and saying, okay, well we can build that for you. And so I don't think that supply chain is being disrupted. I'm just talking about, with Tesla, is like, oh, okay, you need us to build an actuator of this kind of specifications. We need to know ahead of time because we have to get our tooling ready for that, and it takes a little while. And the ramp up, and again, the up in the air question. Ooh, are we going to be doing linear? Or are we not going to be doing linear? Because you might remember that Fast Company article back in the spring that kind of touted the fact that those planetary roller screws are going to be very important, and there's not a whole lot of companies that produce those, and also there's not a whole lot of companies that produce the equipment that produces those, because that's what you really have to look at. It's not how many suppliers I have, is that where do the suppliers get the equipment, the CNC machines and the advanced grinding machines that are needed to produce these things, and can they get them really quickly? Think about the GigaPress. Everyone said, wow, the GigaPress, what a great idea. And it's like, I'll take 10. It's like, back in the line, buddy. You get a bunch of other people, and it takes us like a year or so to be able to build these things. So the backorder time on these things can be pretty long, and that's what happens with the ramp up. These companies are trying to decide: do I invest in the equipment that's necessary for this stuff? Because if you're going to produce a lot of these things, I can't just say I'm going to take one of my machines and run it a little bit longer, or turn some dial and it's a little bit faster. No, these roller screws take on the order of minutes to produce, maybe, and basically single digits per hour is what one machine can produce, and
wow.
that's enough for one actuator, one linear actuator. Not, and you've got 14 of them.
The complexity is seriously on.
You start looking at that and you say, well, wait a minute, if we're going to ramp up, we're going to buy a lot of this equipment. And where's that equipment coming from? Well, there's only a couple of suppliers that are even going to do something like that, because it's such an arcane kind of thing that not that many people need. So that's really why the supply chains have to be informed ahead of time. They've got to get the signal. And they've got to hope that they've locked this thing down and they're talking to suppliers and like cross their fingers when they build the prototype. There aren't all these other issues that they realize, we're going to have to change something in their design.
Let's just go back to the soundbite of Elon that we were listening to.
And it's like, honestly, you look at your hands, you're like, and you move, and if you feel your forearm, like almost all the muscles that control your hand are actually in your forearm, and they're pulling your fingers like puppets. So yeah, there's only a small number of muscles that are in your hand itself. But your hand is all being controlled through tendons that go either through or above your carpal tunnel, and your hand is being operated like a marionette from your forearm. But the limiting factor is the hand.
Very quickly, I also want to play out something interesting he said about the synergies between FSD and Optimus when it comes to AI. Let's listen to this.
Optimus were able to reuse the autopilot computer. So Optimus is intelligence is powered by the AI for the same computer that controls the car, and a small battery pack that's similar to the car battery pack. So there's a lot of similarities with the car, and then the AI that's in the car is similar to the AI that will be in Optimus, running the AI 4 hardware, and then AI 5 hardware when that's ready.
Okay, so you have the biomechanics and the electromechanical challenge, the problem that needs to be solved, and then you have the intelligence, which is the AI. And there's a lot of synergy between Tesla FSD and Optimus, both AI stacks that will look at manipulating the real world and navigating the real world. Would it be safe to say that they're a lot better on the AI front than on the mechanics of it, the electromechanical problem, as Elon put it?
I mean, you need the data. They definitely are building the infrastructure to handle the data, but there are, of course, you could always look at video of people using their hands and gripping things, but I'm not sure. And they've been talking about going from video to nets, so that's good. And
yeah, they've also been talking about sim to real and training on internet-based video, and then using simulation for edge cases and whatnot.
And that's what I thought quite a long time ago about. That's the way to go for training your hand, like picking up the egg, just throw it in the simulator, pick up an egg a million times. That's one way to do it. And looking at the video of picking up an egg, sure, you can get the general shape of your hand and how to approach it, but grit, the strength to not crack it and not drop it, that needs to be run in sim, I'd say, or I'm not even sure.
Or digital twins of environments where Optimus will be deployed for work, like factory floors, etc.
And then the design definitely needs to be finalized, as you mentioned before, Scott, that you can't sim something that is not as one-to-one, perhaps is not required, but at least very close
not so easy
to your product.
Exactly. I would say from the AI, one of the advantages that Tesla probably has is everyone else's inference chips are all energy hogs. I mean, when you think about what you use ChatGPT on and stuff like that, they keep on talking about the amount of energy these things use to be able to solve very simple problems with the inference chip. Tesla very, very early on said, look, this inference chip we have is going to run in the car, and we can't draw more than 50, 70, 100 watts. Otherwise, you're not going to have any range in the car. So they already had to come up with something that was very economical and was able to do it. And that gave them probably a very big advantage when it came to Optimus, because the same problem is like, it's got to be sipping the electrons here. You cannot do it any other way. But while they have like some advantage there, knowing how to design the chip and doing a lot of AI research and everything else, there's a fundamentally very different problem between FSD and Optimus. And this is what I said before. The idea behind FSD is not to interact with the world. The idea of Optimus
exact opposite.
the exact opposite. You know, more degrees of freedom and stuff like that. So now it's coming in contact. The physics and everything else is different. There's a small area of navigation that overlaps. But it turns out the more I'm talking to people about like navigation inside of factories and stuff like that, which you think would have been easily solved problem, like, oh yeah, I mean this SLAM stuff is like it's expensive, it's difficult, and everything else. We can't rely on GPS. You know, it's very different than a mapped road where you have all these other landmarks that you can kind of use to go on there. That makes navigation a bit tricky to say. Also, the you know, your speeds of navigation are very different, which means as far as like obstacle avoidance, the size of your obstacle maps is very different. So if you're in an environment like this, and I have to build my voxels to be very, very small to make sure I can get around every single object that's there. Whereas when I'm driving down the road, I mean, it's like my voxels can be very, very big because I don't even want to come near any of these kind of things. So there are some differences that you're going to sort of see there, that while there are some advantages, it's not like that they have a total advantage over everyone else, because they're also building hardware for the first time that no one else has built. Everyone else is trying to do the same thing, but certainly they do have access to a pretty big supercomputer when it comes. The problem is, you know, they're trying to also solve FSD at the same time, you know, so they don't have it 100% to themselves, but you know, at least it is there.
And they have a lot of cash to throw at the problem. I mean,
right.
That's
now,
something all the startups do.
There were two other things that Elon said there that I'd like to talk to you for a second there, Gustav. You notice he said like, oh, the majority of them, you get a few up in your hand, but he just was very dismissive of
that still worries me. I mean, if you only have this is the motion you would get. I guess in the end it would be like this, and your thumb would just go in there. You would not be able to grip if you did not have the intrinsic, or it would be a very awkward grip. So, and the numbers are actually quite similar. It's if you count the individual, we usually group them like the interos guy, but if you count the individual ones, I think there are actually more muscles in the hand than in the forearm. So it kind of, it worries me. It still worries me a little bit that it's kind of
everything.
There are some down there, but most are here. And I mean, it all depends what you want to use your hand for, of course, to what extent. But showing off the air guitar, and if that's what they're going for, I have a real hard time seeing them achieving that with the Dex. You could probably program it to do a lot of nice motions, but to get the grip strength and stability and putting that all up here, it's going to just add a lot of problems. And
literally, that's air guitar. It's not the actual guitar. The actual guitar, you could apply force.
Exactly.
On the frets.
Air guitar.
You know, that's what they should be fretting about.
So he still stresses me or worries.
You're going to apply force as long as you don't develop corns on your fingertips, because then it's just about. There's a lot less force that you apply on the. The
I mean, you won't be able to. We would not be able to play the guitar, even the basic notes, if we didn't have our intrinsics. It would be really awkward to just do the basic chords on the guitar, and you're probably not gonna sell the bot to play guitar, but we'll see. But it kind of gives the impression that he has not really put himself into this idea. He's heard or seen the anatomy pictures that the muscles are up here, and then kind of left it there, or he's kind of downplaying it to not make people tired of him explaining human anatomy. But it gives
Gustav
me the
just
impression
said the cat amongst the pigeons, didn't he?
But I mean, it feels like he hasn't really gone deep enough into this, and maybe he doesn't have to. It's enough if his engineers does it and presents it to him, because he's good at taking in what his teams are doing and acting upon that. He does not have to know everything perfectly. But
well, Elon, if you're listening, we've got a hand surgeon here. You want to listen to him,
and a robotics expert
and a roboticist.
The other thing is remember a couple of months back when the 1X video came out, and we were watching the hand and going through, and it was making some very funny kind of grasps. And you did an excellent breakdown of that, Gustav, that I ended up turning into a post. You should relink that to anyone that's going in there.
I will. I'll link it below.
The importance of the intrinsics and the reason why you need to have an extensor and everything else, and why their fingers were sometimes doing some really strange kind of movements that were almost indicative of something that was missing in the design. So again, this just comes down to why someone who's a hand surgeon will just look at that and say, this is your problem, and this is what you need to fix it. And it could be that the fixes are pretty simple if you sort of understand exactly how the biomechanics work. Now, this comes to another thing is like I think Elon mentioned in there also the idea of like the hinge joints. So, well, wait a minute, if you're going to take it to the extreme, our hands don't have hinge joints. That IP joint, it's a rolling contact kind of joint that's different. So if you're going to really take it to the extreme that I'm going to be inspired by biomechanics, I'm going to do it exactly the way, it's like, well, get rid of those hinge joints. Why are we engineering hinge joints in there? Because it turns out they're much better, and that biology can't really make a hinge joint because of just biology and everything else. Whereas anyone would tell you that for the most part, a well-engineered hinge joint is going to be superior to one that's just kind of rolling on there. The same thing that I keep on saying, that if you're going to be inspired biology for everything, that we were bio-inspired on coming up with wings for airplanes. Why don't our wings flap on the airplanes?
Yeah, there are better ways to fly.
Because there are better ways to get the thrust that you need. So,
but that's how they started, didn't they? Yeah, the old videos of the guys.
Well, a couple tried doing that because they didn't quite understand it. But eventually, engineers realized that this is another way of doing it. So you can get the inspiration, but at some point you begin to realize that there are things we can do that biology can't, and vice versa. There are things that are really hard for us to do that biology does.
We try and keep it short every time, but we go down the rabbit hole, and this is what happens. Well, thank you, gentlemen, both of you, Scott and Gustav. It's been wonderful catching up with you. There's a lot that people need to understand, a lot of perspective that both of you add to every conversation about Optimus and AI and the biomechanics of it all. I think it's everybody watching should stay grounded, because there's a lot that still needs to be solved. And I'm not just talking about the electromechanical problem, as Elon put it, or the 60% of the problem that's the hand. It's also the supply chains. It's also the AI. It's a whole big challenge that needs to be solved. So it's going to be an interesting journey. And we keep coming back to both of you.
Looking forward to following it.
And thank you, Royden, because a lot of my thesis and understanding exactly how hands and everything come from. Well, I guess this guy over here, assuming that he's on the screen the same way as me, the guy in the middle over here, has really informed me, which again is why I kept on telling people, you got to get a hand surgeon, talk to a hand surgeon, talk to a physical therapist, because they have the knowledge. And so I'm going to say it again: if you're building a humanoid, you've got to go to the people who know exactly how the human body works, and there's plenty of them out there. And professors at universities, everything else. Yeah, you can get a lot from a biomechanics class and stuff like that, but at the same time, I'm not sure that they really go into quite the same detail as what you have someone like a skilled surgeon.
Yeah, the same with Lars' point about building the car, that it might not be the same as thoracic surgery, or as we like to call it, this heart orthopedics. But there are aspects from both sides. And I mean, I don't know engineering or building machines or what kind of actuator would be the best, but I'm guessing if we can kind of get together in a similar form like this,
I mean, you do need an interdisciplinary approach if you have to mimic evolution.
Yes, and we have no choice but to use electromechanical kind of muscles. We cannot create. People are working on it. Eventually, we're going to have an artificial muscle. But till now, we have to use little motors and all the mechanics that goes into taking that spinning motion and turning into whatever we need to do to actuate something.
Absolutely. Great. Thank you very much, gentlemen. Till next time.
You're welcome.